We're going to start taking a look at linear functions 2, the lesson on context and domain and range of linear functions. We're going to start off in the first video talking about context, and then we're going to move on to domain and range and how those represent a graph, especially when there is context involved. So a linear function, again, going back to its roots, is a comparison of two values, or what we might consider variables, which form a straight line pattern. Okay, so it's a comparison of two variables which form a straight line pattern. We've taken a look at some examples in the past where we have numbers that are going up or down by the same value each time. That would be a pattern, and we would consider the first number to be the place value, and then the second number to be the pattern that we are seeing. Again, as one value increases or decreases by a consistent amount, again, always going up or down by the same amount, the other will increase or decrease by a consistent, but not always the same amount as well. Okay, so again, if we have something like have a little chart here that we'll see this, the first number is 5, 6, 7, 8, 9. We're going up by 1 each time, and the sum of the two numbers is going up by 1 each as well. Okay, so in fact, in this case here, both numbers are going up by 1 each time. Doesn't necessarily have to always happen, but it definitely can, and it definitely will be. So what is happening in this pattern here? Well, we have a number here and we have a sum. Okay, so you'll notice that it's not just x and y anymore. Now we have certain values, and when we have those values, these kind of descriptions, then we have often some context involved as well. There is the first number, and if there's a first number, that means there has to be a second number, and there is a sum as well. It looks as though we are adding 4 to the first number to get the sum, right? 5 plus 4 is 9, 6 plus 4 is 10, 7 plus 4 is 11, and on and on and on. So this is some context that is coming into play here. The first number, okay, that I'm putting quotations because that's our title there. The first number is one of the variables. It would be considered the x value. Again, it's in the first spot. It's the x value in the equation. Okay, and the sum column is our second variable. This would be considered the y value in the equation. The equation is the mathematical way of describing the relationship between the two variables. So the mathematical way of describing the pattern that we see, not the context way, the equation is the mathematical way. We're using x and y to describe our first number and our second number. So this here is x, this here is y. How are they related? Yes, we can say it, okay, but we can also show it mathematically as well. Okay? And some of you might kind of see this here. This is x plus 4 is equal to y, or we could write it as y minus 4 is equal to x. There's a couple different ways that we can write that out, but we can write it out as a mathematical equation. Now, when a generic, okay, and you're going to hear me say this word generic often enough as well, equation is given, that means that there's no context. The pattern is based on the variables given in the equation. Okay? So again, when I say generic, we're talking no context involved. It's just an equation. That's it. All we see is the equation. We're talking generic. It's just an equation. Okay? The pattern is then based on the variables that in the equation. When context is given, the variables need to be and can be defined by context as well. Okay, so in this case here, x is the first number that we have. Y is the sum. Okay, so we have a description or a definition for those values. Again, like I said, the previous example defines the x variable as the first number given and the y variable as the sum of presumably the first number and the second number. Okay, so we're just assuming, or at least for the most part, that we have two numbers, because when we have a sum, we are usually using that. We're given the first number. We can assume that the second number is 4 because always first number plus 4 gives us the sum. So therefore, our second number is 4. Doesn't change. It's a constant, but we can use it there. Now, if context is given, the variables in the equation must be defined, and we're going to talk about how to do that, so that anybody reading the equation understands what is being described and what is being described by the equation. Okay, so what does that equation give us? What is it trying to solve for? Okay, that is going to be given in what are the x and the y, and are they defined? Okay, so do we know what they are defined by? So let's take a look at an example here. We're going to look at a few different examples as we go through some contextual problems, and we're going to take a look at how do we put them all together, define the variables, create an equation, then we can give it a point that satisfies the scenario. So number one, we have a class of 23 students is made up of male and female teenagers. Now, we're told something here. We're told that there are 23 students in total, but we're told that it's male and female teenagers. We don't know, okay, how many males and how many females are in the class. Okay, we're not told that. We're just told that the total is 23. Because we're not told how many of each there are, that's going to be our variables. So for the first thing there, we're going to define our variables. We're going to say that x is equal to the number of male teenagers that are in the class, and y is equal to the number of female teenagers that are in the class. Okay, so we're defining our variables. You'll notice very descriptive description or definitions in here. We want to make sure that we know exactly what it is. So here is describing what our variables are. Now, the second part is creating the equation. Now, sometimes the equation is really simple to create. Other times it's a little more difficult to create. In this case here, we have 23 students. We have some males, some females. So to get our total, we do x plus y is equal to 23. Now, you look at this equation, and if it was a generic equation, it would just be a couple numbers that add up to 23. But because we know that they're male and female teenagers, we know that this is the number of male teenagers plus the number of female teenagers equals 23 total students in the class. Okay, so that's what we know with that there. Now, the third part to this all, coming up with a value that works, okay, or a point that satisfies the scenario. We're looking for values of x and y which satisfy. Well, we could have 11 males and 12 females. That's one that works. We add them together, it's 23. There's some males, some females. Okay? Now, it doesn't say that it could also be like 023 or 23-0, or really anything that's a part of that. The one thing, though, that you have to be aware of is in a generic one, we could have like decimals, but in this context here, we cannot have a decimal number of male or female students, so it has to be whole numbers, which we're going to talk a little more about when we get into domain and range a little bit later on in this lesson. So let's do a few more examples here. Number 2, Emily is 4 years older than her sister Tricia. All right, well, we do not know, okay, how old Emily or Tricia are. We do know that the difference is 4 years. So for part 1, we're looking to define our variables. X is going to be Emily's age, and we could say in years. And Y is going to be Tricia's age in years. Again, notice the specific definitions to make sure that we know exactly what they represent. Someone should be able to read what you are doing and know exactly what you were talking about without ever knowing what the question was about. Okay, so that's what you should be able to show in your work. Now it says that Emily is 4 years older than her sister. So if we take Emily's age and we subtract 4, we are going to get Trisha's age. Or on the same note, we could take Trisha's age and we could add 4, and that will give us Emily's age. Both of these work. They in fact they're exactly the same, but mixed around a little bit. Or sorry, they mean the same thing, but they're mixed around a little bit. So this would be the equation that we're coming up with. Now, what is a point that works? Well, let's say that Emily is 12. If Emily is 12, we know that 12 minus 4 is 8. That means that Trisha is 8. Okay, that would be a description of, a point that would work in this scenario. Now, it's not the only one, because we know that when Emily turns 13, then Trisha will be 9. When Emily's 14, Trisha's 10. Okay, those are all ones that work. And again, we're not kind of told how far apart they are, or if they are, kind of in what case that is, but we're not going to deal with decimals. We're just going to deal with age in years. All right, number 3, define the variables. Okay, so we're going to find what is X, what is Y. Well, here we go. There are 3 times as many cars on the road as trucks. 3 times as many cars on the road as trucks. We don't know how many cars and we don't know how many trucks. So we're going to say that X is the number. I'm going to use that little thing there, little number symbol. It's not a hashtag, it's number. Number of cars on the road. And Y is the number of trucks on the road. Now, to come up with an equation for this is a little bit trickier, but when we see something about times or divide or something like that, we are multiplying one of our variables by a number. In this case here, we're going to multiply it by 3. Now, it's very common to take 3 and multiply it by the number of cars, but in fact, there are 3 times as many cars on the road, so the only way that we can make these two equal, and I'll put it like this here, the only way we can make those two equal is if we multiply the number of trucks by 3, and that'll equal the number of cars. So when we're multiplying, when we're given something like 3 times as many, we're always multiplying the opposite variable. Okay, we're not multiplying the cars, we're multiplying the trucks. Because, and let's look at an example here that works. Let's say that there are 10 trucks. We multiply that by 3, that means there are 30 cars on the road. Okay, so if we're multiplying the number of trucks by 3, we get 3 times as many cars. Okay, that's how we have to write out as an equation. We're not multiplying the cars, because if we multiply 30 times 3, we're getting 90 trucks, and we know that that's not proper. So we have to do exactly the opposite multiplication in there. All right, number 4, trail mix has half as many M&Ms as peanuts. Well, we don't know the number of M&Ms in trail mix. Or, well, this is X is equal to, and this is Y is equal to the number of peanuts. Now, if you ask me personally, I think that there should be more M&Ms than peanuts, but that is my personal opinion, and I'm sure they wouldn't make as much money on that, and I guess I could just go buy a bag of M&Ms then. All right, so we got the number of M&Ms and the number of peanuts. Second part, we need to come up with our equation. There are half as many M&Ms as peanuts, so we take the number of peanuts divided by 2, and that's going to equal the M&Ms. Or, in this case here, we could actually multiply our number of M&Ms by 2, and that's going to equal to our number of peanuts. Okay, so these are a couple different ways that we can write it. There's half as many, so if we multiply by 2, we get the answer. An example. Let's go a little bit crazy here. Let's say that we have 56 peanuts. Well, it's going to be half that, so we divide this by 2. That'll be 28 M&Ms. So this is how we can go through that. Now, if you're following along for class, you can take a look at assignment LI.02, numbers 1 to 4. Numbers 1 to 4 is based on context, okay, contextual questions, and coming up with defining our variables, determining what is our equation, and then what are some of the answers that we can come up with from that.